Hello there, and welcome back to the Sleepy Explainer, where science is told slowly and softly, like a bedtime story for curious minds. Tonight, we're going to travel back hundreds of millions of years, to the time when almost all of Earth's land was joined into one. That land was Pangea. And across this video, I'll share 180 strange facts about it, things you may not have known, but will carry with you after tonight. If you enjoy drifting through deep time like this, consider liking and subscribing. It really helps this sleepy little channel grow. So, let's begin with our first fact. Pangea wasn't the first supercontinent. Earth's crust works in long cycles. Continents don't stay put. They collide, merge, and then split apart again. Before Pangea, there were others, Rodinia, about 1 billion years ago, and Nuna before that. Pangea was just the latest in a repeating rhythm that may continue into our future. Fact 2. Pangea began forming about 335 million years ago. At that time, the land masses we now call Africa, South America, North America, and Eurasia were slowly moving together. Each collision raised new mountains and closed ancient seas until all the world's land was pressed into one vast shape. And fact 3, Pangea stayed together for a long time, around 160 million years. To give that scale, the dinosaurs appeared, evolved and spread across Pangea, all while it remained whole. It lasted far longer than the time between the age of dinosaurs and today. Already these 3 facts show us something important. Pangea wasn't unique, but it was extraordinary. It was the setting for some of the most dramatic events in Earth's story. And it lasted long enough to leave scars we can still see in mountains, coastlines, and fossil trails. And that brings us to our next step. How do we know Pangea existed at all? That's where we'll head in the next segment. And that question, how do we know Pangea existed at all, brings us to our next strange set of facts. Fact 4. The world ocean around Pangea was called Panthalassa. Imagine one immense body of water covering 70% of Earth, wrapping completely around the single landmass. Scientists use fossilized corals, chemical traces in rocks, and oceanic crust to reconstruct Panthalassa's scale and currents. It wasn't just background scenery. It shaped the climate, migration of life, and even how winds carried across Pangea. Fact 5. The name Pangea comes from the Greek words for all Earth. It was chosen in the early 20th century by Alfred Wegener, the scientist who first argued that continents drift. At the time, most experts thought continents were fixed. Wegener noticed something many had overlooked. Africa and South America fit together almost perfectly, like pieces of a broken plate. But he went further. He collected evidence from geology, paleontology, and climate patterns to show they must have been joined. Fact 6. Fossils provided the proof. Wegener pointed to remains of the same plants and animals found on continents now separated by thousands of kilometers of ocean. Glossopteris, a fern-like plant, left fossils in both South America and Africa. Mesosaurus, a freshwater reptile, appears in fossils in South America and southern Africa, but nowhere else. These fossils don't make sense on separate continents. On one unified landmass they do. Wegener's idea of continental drift was mocked at first. He didn't know how continents could move, only that the evidence said they did. It took another 50 years before plate tectonics provided the mechanism. Earth's crust is split into moving plates that ride atop the mantle. With that discovery, Pangea went from speculation to established fact. So already, with just a few strange facts, we've learned that Pangea was more than a name. It was surrounded by a global ocean. It was recognized thanks to careful fossil studies, and its discovery rewrote Earth science completely. And here's where things grow even more curious. If all the continents were once fused, what did this immense land actually look like? What kind of geography did all Earth have? That's where we go next. So now that we know Pangea was real, proven by fossils, geology, and the science of drifting plates, the next question is, what did it actually look like? Fact 7. Pangea covered about a third of Earth's surface. That doesn't sound like much until you realize it meant nearly every continent you know today: Africa, South America, North America, Europe, Asia, even India and Antarctica were welded together into one continuous landmass. From pole to pole there was no ocean barrier. To walk from modern-day Brazil to what would one day become Siberia, you could stay on dry land the entire way. Fact 8. The interior of Pangea was one of the harshest places Earth has ever known. Being so vast, much of it lay far from the moderating influence of the ocean. Rain rarely reached the middle. Deserts spread across central Pangea, with temperature extremes far greater than anything we see today. Geological evidence from sandstones and fossil dunes in present-day North America shows that these desert systems were some of the largest in Earth's history. Fact 9. Pangea stretched from the northern polar regions to the southern ice sheets. This meant climates varied enormously. The north could be frozen while the south baked under desert heat. Coastal regions, by contrast, were wetter and more temperate, with rivers, lakes, and forests. In other words, Pangea contained almost every environment on Earth within a single connected landmass. Scientists know this by studying rocks, sediments, and fossilized soils. Layers of sandstone tell us about deserts. Coal seams reveal where swampy forests once grew, and glacial deposits scattered across multiple continents show that ice covered parts of Pangea's southern edges. Together, they paint a picture of a world of extremes, unified land but fractured climates. And this leads to another strange fact. When you squeeze so much land into one place, the collisions don't just create deserts, they also build mountains, huge ones, some of which still tower over us today. That's where our story drifts next. We've seen Pangea's mountains rise from collisions, but the story of its surface doesn't end with peaks and deserts. Wherever mountains form, rivers soon follow, and in Pangea, those rivers carved vast networks across the supercontinent. Fact 13. Pangea contained some of the largest river systems in Earth's history. When Africa collided with North America, not only did the Appalachians rise, rivers spilled from them, flowing across hundreds of kilometers into inland basins. These rivers carried silt, sand, and nutrients, leaving behind thick sedimentary deposits we can still study today. In places like present-day Pennsylvania, geologists read these rock layers as the ancient signatures of rivers that once crossed the heart of Pangea. Fact 14. Inland seas expanded and shrank within the supercontinent. Because so much land was connected, tectonic shifts often created shallow basins that filled with water. These seas could stretch for hundreds of kilometers, acting like inland oceans. Fossilized shells, corals, and marine sediments found in parts of modern-day Europe and North America are evidence of these temporary seas. Some vanished as quickly as they appeared, leaving behind thick salt beds, geological proof of their evaporation. Fact 15. Lakes in Pangea were immense, long-lasting, and crucial to life. Unlike today's continents where many lakes are isolated, Pangea's rift valleys and fault zones created giant depressions that held fresh water. These lakes became cradles for amphibians, early reptiles, and plant ecosystems. Fossil fish and amphibian remains preserved in lake sediments show that these freshwater habitats were hotspots of biodiversity. Taken together, Pangea's rivers, lakes, and seas tell us something important. The supercontinent wasn't only deserts and mountains, it was dynamic, constantly shifting between wet and dry, saltwater and freshwater. Its waterways linked ecosystems, gave early reptiles migration routes, and left behind resources like salt, coal, and fertile soil deposits that still shape our landscapes today. And with rivers and seas laid out, another question rises. What kind of skies hung over this ancient land? What was the atmosphere like in a world where everything was connected? That's where we'll head in the next chapter. If the land of Pangea was harsh and varied, its skies were just as extreme. The atmosphere itself was different from today's world, and it left fingerprints in the rocks, in fossils, and even in the size of the creatures that crawled and flew. Fact 16. Pangea's atmosphere had unusually high oxygen levels. During the late Paleozoic and early Mesozoic, oxygen made up as much as 30 to 35% of the air, compared to today's 21%. This change is recorded in trapped air bubbles within ancient minerals and in the chemistry of fossil soils. Higher oxygen allowed insects and arthropods to grow to sizes that would be impossible now, because they rely on diffusion rather than lungs. It's why dragonflies in Pangea could reach wingspans of 70 centimeters. Fact 17. The supercontinent created climate extremes unlike anything on modern Earth. Because so much land was gathered together, the interior of Pangea was dry, with scorching summers and freezing winters. By contrast, the coasts were wetter, with heavy seasonal rains. This contrast created what scientists call mega monsoons, vast storm systems that circled the continent and shaped ecosystems on a continental scale. Evidence of these storms is preserved in thick layers of mudstone and ripple-marked sands that point to seasonal flooding. Fact 18. Glaciers still clung to Pangea's southern regions. Even while much of the continent was dry and warm, parts of Gondwana, what would later become Antarctica, South America, Africa, and India, were covered by ice sheets. Drop stones, glacial scratches on bedrock, and deposits of till show that ice advanced and retreated across southern Pangea multiple times. The coexistence of glaciers and deserts within one landmass made Pangea one of the most climatically diverse places Earth has ever seen. Together, these facts remind us that Pangea was not a uniform land. It was a patchwork of extremes, from insect-filled forests thriving under oxygen-rich skies, to deserts baked by heat, to ice sheets grinding across the south. Its atmosphere shaped life, landscapes, and even the resources that would one day fuel human industry. And if the skies could be that different, what about the forces below? Beneath Pangea, tectonic stress was building, and volcanoes would soon play a dramatic role in shaping the supercontinent. That's where we'll turn next. We've looked at Pangea's deserts, mountains, rivers, and skies. But what about what lay beneath? Supercontinents don't stay stable forever. While Pangea seemed solid on the surface, deep below, heat and pressure were building, and the Earth was preparing for violent change. Fact 19. Pangea was marked by rift valleys that foreshadowed its breakup. A rift valley forms when tectonic plates pull apart, stretching and thinning the crust. Geologists have found evidence of these rifts in the eastern United States, northwestern Africa, and parts of Europe. They began as cracks that filled with lakes, swamps, and volcanic flows. These fractures were the first whispers that Pangea would not last forever. Fact 20. Volcanic activity surged across the supercontinent. As Pangea shifted, magma pushed upward, spilling lava across thousands of square kilometers. Some of these eruptions created basalt plateaus still visible today, like the Central Atlantic Magmatic Province. These volcanic outpourings released massive amounts of carbon dioxide into the atmosphere, influencing global climate for millions of years. Fact 21. Pangea's volcanism was tied to one of Earth's greatest extinctions. The end Triassic extinction, which wiped out around 75% of species, coincides with colossal eruptions as Pangea began to rift. The gases from these volcanoes warmed the planet, acidified oceans, and destabilized ecosystems. Without this event, dinosaurs might never have risen to dominance. So beneath Pangea's surface, fire was always present, carving valleys, pouring lava, and releasing gases that shaped both climate and life. The supercontinent may have looked eternal from above, but deep down it was already being pulled apart. And if volcanoes could alter the course of evolution, imagine what life was like on this land before those disasters struck. What kinds of creatures actually lived and thrived across Pangea? That's where we'll journey next. If volcanoes and shifting plates were reshaping the land, what was happening on the surface of Pangea? The supercontinent wasn't empty, it was alive, filled with creatures adapting to its strange and extreme conditions. Fact 22. Pangea was home to the early ancestors of dinosaurs. During the Triassic period, small, agile reptiles known as archosaurs began to spread. Fossils from South America, Africa, and Europe show that these early archosaurs were already experimenting with body forms that would one day lead to the dinosaurs, crocodiles, and even birds. Their ability to survive in both dry deserts and wetter coasts gave them an edge in a world of extremes. Fact 23. Giant amphibians thrived in Pangea's rivers and lakes. Creatures like Metaposaurus stretched nearly 3 meters long, resembling crocodiles but belonging to an older lineage. Their fossils are found in what is now Europe and North America, proof that freshwater ecosystems stretched across the supercontinent. These amphibians were top predators in their watery habitats until reptiles began to dominate. Fact 24. Insects reach gigantic sizes in Pangea's oxygen-rich air. We've already mentioned dragonflies with wingspans over 0.5 meter, but there were also massive millipede-like arthropods such as Arthropleura, which grew up to 2.5 meters long. These colossal creatures scuttled through the forests, feeding on plants and decaying matter, shaping the ecosystems just as much as the larger reptiles did. Together, these creatures made Pangea a place of experimentation. Amphibians ruled waterways, archosaurs were laying the foundations for future dominance, and insects grew to scales we can hardly imagine today. The fossil record across continents, identical species found on opposite sides of the Atlantic, confirms just how unified life was on this ancient land. But the story of Pangea's life wasn't only about survival, it was about opportunity. With no oceans blocking migration, animals could roam freely, spreading across the entire landmass. This freedom created a stage where entire groups of creatures could rise, diversify, and sometimes vanish entirely. And that raises the question, how did plants shape these ecosystems? What did the forests, swamps, and landscapes of Pangea actually look like? That's where we'll wander next. If archosaurs, amphibians, and giant insects filled Pangea with motion, then plants filled it with life. Without vast forests, riverside ferns, and swampy wetlands, none of those animals could have thrived. The landscapes of Pangea weren't just backdrops, they were ecosystems as complex and important as any jungle or grassland we know today. Fact 25. Pangea's forests were dominated by gymnosperms, cone-bearing plants like conifers, cycads, and ginkgos. Unlike flowering plants, which hadn't evolved yet, these gymnosperms used cones to spread their seeds. Fossilized trunks and pollen grains show that they covered much of the supercontinent, forming dense forests along coasts and river valleys. Fact 26. The interior deserts of Pangea supported only hardy plants. With little rainfall and extreme temperatures, central Pangea was largely barren, broken by patches of drought-resistant ferns and shrubs. Fossil soils, called paleosols, reveal that roots often spread shallowly, suggesting plants had to survive on minimal water, much like desert plants today. Fact 27. Coal deposits in modern North America, Europe, and Asia come from Pangea's swamp forests. In wetter regions, especially near rift valleys and inland seas, thick mats of vegetation grew in swampy ground. Over millions of years, layers of plant material compacted into peat and eventually transformed into coal. This is why so many coal seams around the world date back to the Carboniferous and Permian periods when Pangea was forming. These forests didn't just provide food and shelter, they created the oxygen-rich atmosphere that allowed giant insects and amphibians to thrive. They stabilized soils, influenced rainfall, and left behind resources still fueling our modern world. So when you imagine Pangea, don't just see deserts and dinosaurs. Picture forests of conifers stretching for hundreds of kilometers, swampy wetlands echoing with amphibian calls, and dry interiors dotted with hardy plants clinging to survival. And if plants shaped the land so strongly, how did life migrate across such a vast, connected continent? That's the question we'll explore next. If Pangea's forests and swamps created the stage, then migration was the play unfolding across it. On today's Earth, oceans divide species into separate continents, but in Pangea, no such barriers existed. For millions of years, animals and plants could move freely across an unbroken world. Fact 28. Pangea allowed species to spread across entire hemispheres. Fossil evidence shows the same species of reptiles, amphibians, and plants appearing in South America, Africa, India, and even Antarctica. This wasn't coincidence. It was the direct result of a unified landmass. For example, Lystrosaurus, a tusked herbivore, spread widely across Pangea after the Permian extinction, surviving in regions that today are separated by oceans. Fact 29. Migration shaped the evolution of early dinosaurs. Because herds of archosaurs and proto-dinosaurs could travel vast distances, genetic mixing was greater, and adaptations spread quickly. This meant evolutionary experiments didn't stay isolated. Traits like upright walking, new tooth shapes, and even herd behavior could spread across the continent in relatively short geological time. Fact 30. Pangea's open land created ecological connections unlike anything today. Picture a river basin in what's now Africa flowing into a swamp in modern-day Europe, supporting the same insect species, amphibians, and early reptiles. The fossil record reveals ecosystems that stretched across what we think of today as separate continents. Migration made Pangea one of the most interconnected biospheres in Earth's history. This freedom of movement also meant vulnerability. A disease, drought, or predator could affect species across enormous distances. That interconnectedness made life resilient in some ways, but fragile in others. A balance we still see in global ecosystems today. So Pangea wasn't just a supercontinent of stone and soil, it was a supercontinent of life, with highways of rivers, plains, and forests where creatures spread, adapted, and transformed. And if migration unified Pangea's ecosystems, what happened when the supercontinent began to tear apart? That's where the next stage of the story takes us. Up to now, we've seen Pangea at its peak. Forests sprawling, animals migrating freely, rivers and deserts shaping life. But no supercontinent lasts forever. Beneath its surface, tectonic forces were already pulling at the seams, and slowly cracks began to spread. Fact 31. Rift valleys marked the beginning of Pangea's breakup. These weren't small features, they were immense gashes in the Earth's crust where the land stretched and sank. One of the most famous examples is visible today in the Newark Basin of the eastern United States. Once part of Pangea's rift system, it holds thick layers of red sandstone and lava that tell us exactly when the land began to tear. Fact 32. The Central Atlantic Magmatic Province was born from this fracturing. Around 200 million years ago, some of the largest volcanic eruptions in Earth's history poured lava across what is now eastern North America, northwestern Africa, and parts of Europe. These basalt flows covered millions of square kilometers, leaving behind thick volcanic rock we can still study. They were not isolated events, but global signals of a continent in transition. Fact 33. These eruptions triggered a mass extinction. As carbon dioxide and sulfur dioxide filled the air, global climates shifted violently. Oceans acidified, temperatures spiked, and ecosystems collapsed. Roughly 75% of species vanished, including many reptiles that had dominated the Triassic. With them gone, dinosaurs had the opportunity to rise to dominance in the Jurassic. So the breakup of Pangea was not just a geological event, it was biological, ecological, and evolutionary. The first cracks didn't just split the land, they rewrote the rules of life on Earth. And as the land masses drifted, they didn't just create new boundaries, they reshaped oceans, climates, and even the future of biodiversity. That's the journey we'll follow next. The first cracks in Pangea were only the beginning. Over millions of years they widened, filled with water, and became the foundations of the oceans we know today. What had once been a single unified landmass was now breaking into pieces, and with that, Earth itself began to look more familiar. Fact 34. The Atlantic Ocean was born from Pangea's rifting. As North America pulled away from Africa and Europe, the gap between them filled with seawater. At first, it was North America, Africa, Antarctica, India, and Australia. The northern bloc, Laurasia, held North America, Europe, and Asia. For the first time in over 100 million years, Earth's landmasses were divided into separate clusters, reshaping climate and evolution. This wasn't an overnight event. It unfolded slowly, like a book being pried open, page by page. The rift valleys deepened, lava spilled across their edges, and water surged in to carve out the first true shorelines. Entire ecosystems were split apart. What once roamed freely across Pangea now faced new barriers, and as the continents drifted, the oceans they created did more than divide. They became engines of climate, circulation, and evolution. In the next stage of Pangea's story, we'll see how these new oceans transformed not just geography, but life itself. When the first waters poured into Pangea's rift valleys, they did more than split land apart. They created new engines for Earth's climate. Oceans are not passive features. They drive winds, storms, and temperatures. And as the Atlantic widened, the climate of the planet shifted in dramatic ways. Fact 37. Ocean circulation began redistributing heat globally. During Pangea's time, the interior of the continent was extremely dry and hot. But once the Atlantic opened, new coastlines brought moisture inland, changing ecosystems. Warm currents carried heat toward the poles, while cold currents drew oxygen into the seas. This circulation created more habitable zones for marine and coastal life. Fact 38. Shorelines multiplied, boosting biodiversity. A single supercontinent meant fewer coastlines, but as Pangea broke apart, shorelines expanded dramatically. More coasts meant more shallow seas, lagoons, and estuaries, perfect environments for evolution. Fossil evidence shows bursts of new marine species during this period, thriving in the fresh habitats created by shifting seas. Fact 39. Ocean chemistry shifted with volcanism. Massive eruptions tied to the breakup pumped carbon dioxide into the atmosphere, which dissolved into the seas, raising acidity levels. This reshaped marine life, wiping out some groups but allowing others, like ammonites and early marine reptiles, to diversify and dominate. The breakup of Pangea wasn't just continental drift. It was the beginning of an entirely new ocean-driven climate system. Winds shifted, rains returned to places that had been deserts for millions of years, and coastlines buzzed with new forms of life. And if oceans could transform climates and fuel biodiversity, what did this mean for the rise of entirely new groups of animals? That's the story we'll follow next. As Pangea's supercontinent shattered and oceans carved new coastlines, life adapted quickly. The changing climate didn't just alter landscapes, it created opportunities. Out of shifting seas, rising forests and expanding plains, new animals rose to dominance. Fact 40. Dinosaurs began their true expansion after Pangea's breakup. The Triassic extinction had cleared the stage, and as ecosystems rebuilt, dinosaurs filled niches left behind. Fossils across Gondwana and Laurasia show how quickly they spread, adapting into carnivores, herbivores, and everything in between. Within a few million years, dinosaurs were the defining land animals of the Jurassic. Fact 41. Marine reptiles surged in diversity. With more shorelines and shallow seas, reptiles like ichthyosaurs, plesiosaurs, and nothosaurs took over the oceans. Their fossils are found across Europe, North America, and Asia, proof of how widespread they became. These creatures weren't dinosaurs but evolved alongside them, ruling the seas as dinosaurs ruled the land. Fact 42. Mammal ancestors emerged in the shadows. While dinosaurs dominated above, tiny shrew-like creatures, early mammalia forms, began to carve out niches at night. Their fossils, found in Triassic and Jurassic layers, show traits like fur and differentiated teeth. They remained small for millions of years, but they carried the evolutionary seeds that would one day shape our own lineage. This was the great reshuffling of life after Pangea. The supercontinent's unity had allowed species to roam freely. Its breakup fractured habitats, forcing adaptation and specialization. What once was a single world became many, and each split gave rise to new evolutionary paths. And if life could respond so dramatically to shifting continents, what about the plants? How did vegetation adapt to this newly divided Earth? That's where our story turns next. As dinosaurs expanded and reptiles conquered the seas, another quiet revolution unfolded in the plant world. Pangea's forests, swamps, and deserts had once been unified, stretching across thousands of kilometers. But as the continents drifted apart, so too did the ecosystems, forcing plants to adapt and specialize in brand new environments. Fact 43. Conifers dominated the early Jurassic forests. With their ability to tolerate a range of climates, conifers thrived on both Gondwana and Laurasia. Fossilized pine-like needles and trunks are found across North America, Europe, and Asia, showing how these trees formed the backbone of newly emerging ecosystems. Fact 44. Cycads and ginkgos spread widely, becoming living fossils. These hardy plants, with their thick leaves and slow growth, flourished in both tropical and temperate regions. Some of their lineages survive today, with modern cycads and ginkgo trees almost identical to their Jurassic ancestors. Their persistence makes them some of the most remarkable survivors of Earth's deep time. Fact 45. The breakup of Pangea isolated plant species, leading to regional diversity. Before the split, gymnosperms were globally widespread, but as continents drifted, climates diverged, and plants began to adapt to local conditions. This isolation explains why today's continents have such distinct vegetation patterns. The first steps of that divergence were already underway in the Jurassic. For animals, plants weren't just scenery, they were life support. Forests provided food, cover, and even the oxygen that made ecosystems possible. Each continental fragment carried its own green kingdom, reshaping habitats for millions of years to come. And just as plants diversified in the wake of separation, the oceans themselves were becoming testing grounds for evolution. The marine world was about to host its own wave of strange and spectacular experiments. While forests divided and new plant lineages took root on land, the seas that opened between continents became laboratories of evolution. With new coastlines, shallow seas, and vast open waters, marine ecosystems flourished in ways Earth had never seen before. Fact 46. Ichthyosaurs reached their golden age. These dolphin-like reptiles were among the fastest predators of the Jurassic oceans. Fossils from Europe and North America reveal streamlined bodies, massive eyes for hunting in deep waters, and stomach contents filled with fish and squid. Some species grew longer than a bus, patrolling the seas as apex predators. Fact 47. Plesiosaurs and pliosaurs rose as dominant marine hunters. With their long necks or massive skulls, they filled niches across the oceans. Plesiosaurs used flexible necks to snatch fish in shallow waters, while pliosaurs, like Liopleurodon, grew to terrifying sizes, capable of preying on other marine reptiles. Fact 48. Ammonites became key markers of time. These coiled-shelled cephalopods weren't just abundant, they were diverse, adapting rapidly to changing seas. Paleontologists use ammonite fossils to date Jurassic rocks worldwide, making them one of the most important index fossils in geology. Together, these creatures turned the oceans into alien worlds of their own, filled with giant hunters, swirling schools of fish, and cephalopods drifting through reefs. Unlike the fragmented ecosystems of land, the seas remained interconnected highways, allowing marine reptiles and ammonites to spread across Gondwana and Laurasia alike. And while the oceans surged with life, something far more subtle was happening high above, in the skies. The first flying reptiles were taking to the air, opening yet another chapter in Earth's evolutionary story. While oceans filled with predators and continents teemed with forests, another frontier was opening above, the skies. For the first time, vertebrates had learned to truly fly, and their arrival reshaped ecosystems forever. Fact 49. Pterosaurs were the first vertebrates to conquer the air. Appearing in the late Triassic but flourishing during the Jurassic, these flying reptiles developed wings supported by an elongated fourth finger. Fossils like Dimorphodon and Ramphorhynchus show a wide range of adaptations, from short-tailed gliders to long-tailed flyers with aerodynamic crests. Fact 50. Some pterosaurs were as small as sparrows, while others grew to the size of small planes. By the Jurassic, species like Pterodactylus dominated coastal cliffs, diving for fish. Later relatives like Quetzalcoatlus, though from the Cretaceous, show how far this lineage pushed the limits of size, with wingspans exceeding 10 meters. Fact 51. Their bones reveal extraordinary adaptations for flight. Hollow, lightweight skeletons, keeled breastbones for strong wing muscles, and hair-like pycnofibers for insulation gave them both endurance and maneuverability. These adaptations foreshadowed what birds would later perfect. In the skies above Pangea's remnants, pterosaurs weren't just novelties. They were active predators, scavengers, and competitors. Their presence connected ecosystems, linking land, sea, and air into a three-dimensional web of life. And while the skies were alive with these new pioneers of flight, another evolutionary story was quietly building momentum on land. The early ancestors of birds. But before we reach them, we need to see how Pangea's breakup influenced the climate patterns that made these new worlds possible. The breakup of Pangea wasn't just a geological story, it was also a climatic revolution. As continents shifted into new positions and seas deepened, wind and rainfall patterns reorganized the planet's climate belts. Fact 52. Arid zones shrank as oceans spread. During the height of Pangea, much of the interior was desert, cut off from oceanic moisture. But as rifts widened and coastlines multiplied, rains reached deeper inland. Fossil pollen records show wetter environments replacing deserts, allowing lush forests to expand. Fact 53. Latitudinal climate belts became more defined. With continents drifting, Earth's tilt and rotation began producing clearer bands of tropical, temperate, and polar climates. This structure, familiar to us today, began to emerge during the Jurassic and Cretaceous as continental placement guided atmospheric circulation. Fact 54. Mountain building events amplified climate contrasts. As India began its long drift toward Asia, early tectonic collisions created uplifts that disrupted wind patterns. Similar events in other regions show how even small mountain ranges could redirect rainfall and create rain shadows, shaping ecosystems on a continental scale. For life, these climate changes meant constant adaptation. Species that once roamed vast uniform landscapes now faced fragmented worlds with diverse environments. Some thrived in the new temperate belts, others specialized in tropical coasts. This growing mosaic of habitats fueled biodiversity, ensuring Earth would never return to the uniformity of a single supercontinent. And if the land and air were undergoing such dramatic changes, what about the oceans themselves? The currents that had once stabilized climates were now evolving into systems that looked more and more like the modern world, and with them came new evolutionary opportunities. With continents drifting apart and climate belts settling into new patterns, the oceans became the invisible architects of Earth's future. They weren't just vast bodies of water, they were engines of motion, heat, and nutrients. And as Pangea broke down, the very currents of the seas began to resemble those of our modern world. Fact 55. The Proto-Atlantic created the first trans-ocean circulation. As rifts widened between Africa and North America, water flowed freely into the basin, generating currents that carried heat and nutrients from one side of the ocean to the other. This was the beginning of a system that millions of years later would become the Gulf Stream. Fact 56. Shallow epicontinental seas amplified biodiversity. As continents split, shallow seas covered wide areas of Europe, Asia, and North America. These warm, nutrient-rich waters were nurseries for ammonites, fish, and marine reptiles. Their expansion created evolutionary hotspots where life flourished. Fact 57. Ocean chemistry balanced ecosystems. Volcanism released vast amounts of carbon dioxide and much of it dissolved into the seas. This could have turned oceans toxic, but circulation currents distributed oxygen and nutrients, preventing widespread collapse. In a sense, the breakup of Pangea created a more resilient global ocean system. These shifting waters did more than sustain life. They connected continents. They spread species across vast distances, linked ecosystems, and stabilized climates. The Earth was no longer one giant landmass with an interior cut off from the sea. It was becoming a true planetary network, held together by currents that touched every shore. And while the oceans shaped life below, high above them another revolution was quietly stirring, one that would eventually give the world its very first birds. While pterosaurs had already claimed the skies, a different branch of reptiles, the dinosaurs, were quietly reshaping themselves for flight. Their journey from ground-dwelling hunters to the ancestors of modern birds is one of evolution's most extraordinary transformations. Fact 58. Archaeopteryx marked the turning point. Discovered in Germany's Solnhofen limestone, this 150-million-year-old fossil had both reptilian features, teeth, claws, a long bony tail, and avian traits like feathers and wings. It is widely considered the first true bird bridging two worlds in one skeleton. Fact 59. Feathers evolved before flight. Fossils of small theropod dinosaurs show that feathers first developed for insulation or display, not for flying. Only later were they co-opted for gliding and powered flight. This means the bird lineage was experimenting with feathers long before Archaeopteryx ever flapped its wings. Fact 60. Birds rose in tandem with changing environments. As Pangea fractured and ecosystems diversified, niches opened for small, agile insect eaters and fish hunters. Early bird-like species filled those roles, spreading into forests, coastlines, and wetlands, where their wings gave them survival advantages over other small reptiles. The skies now held two great lineages, pterosaurs and birds. But unlike the pterosaurs, birds would carry their evolutionary torch forward, adapting into thousands of forms that survive to this day. Their humble beginnings in the shadow of Pangea remind us that even in eras dominated by giants, small creatures with bold adaptations could shape the future. And while the skies filled with wings, the earth beneath was still restless. Volcanoes, rifts, and shifting continents continued to sculpt the planet, preparing for the next great act of Earth's story. Even as forests spread, oceans connected, and birds flapped their first uncertain wings, the Earth beneath remained restless. Pangea's breakup wasn't a quiet drift, it was driven by fire. Beneath the crust, plumes of molten rock surged upward, cracking the land apart, feeding volcanoes and reshaping the surface in ways that would ripple through life itself. Fact 61. The Central Atlantic Magmatic Province was one of Earth's largest volcanic events. Around 200 million years ago, immense lava flows erupted across what is now eastern North America, western Africa, and parts of Europe. These eruptions left behind basalt plateaus that still stretch for thousands of kilometers, silent reminders of the power that split continents apart. Fact 62. Volcanism released massive amounts of greenhouse gases. Carbon dioxide and methane poured into the skies, triggering rapid climate shifts. Geological evidence shows spikes in atmospheric CO2 at this time, linked to global warming events that stressed ecosystems on land and in the oceans. Fact 63. These eruptions played a role in mass extinctions. At the end of the Triassic, many reptile groups and marine species vanished, unable to survive the sudden environmental upheavals. The survivors, including dinosaurs, mammals, and early birds, inherited a transformed planet where volcanic scars marked the landscape. This fiery backdrop wasn't just destruction, it was also creation. Volcanic ash-enriched soils helping forests rebound. New coastlines and rifts offered fresh habitats for life to explore. In a sense, Earth's violence cleared the stage for new evolutionary experiments. And as the land continued to crack and spread, the oceans themselves began forming circulation systems that tied climates and continents together even more tightly. Systems that would eventually resemble our modern global ocean conveyor belt. Beneath the fiery skies and across the widening rift valleys, the oceans were quietly undergoing their own revolution. As continents moved apart, basins deepened and seaways opened, setting the stage for a circulation system that would one day stabilize Earth's climates. The first stirrings of the global ocean conveyor belt. Fact 64. Narrow rift seas funneled water into powerful currents. Where Africa and North America separated, seawater rushed in and created consistent flows. These young currents transported heat across latitudes, helping regulate climates far beyond the rift zone. Fact 65. Deep water formation zones began to emerge. With cooler polar waters forming in the south, denser currents sank and drove circulation on a scale the planet had never experienced before. This vertical overturning connected surface and deep waters, distributing nutrients across entire oceans. Fact 66. Early conveyor circulation stabilized ecosystems. Fossil records show bursts of marine biodiversity linked to nutrient cycling in shallow seas. plankton blooms fed by upwelling currents supported food chains that stretched from tiny organisms to colossal marine reptiles. Though still primitive compared to today's global thermohaline circulation, these systems reshaped Earth's future. Oceans weren't just passive basins anymore. They became dynamic regulators of climate and life. And just as the seas were settling into their rhythm, the land was far from calm. The continents themselves were continuing their drift, carving the outlines of the world we recognize today. The breakup of Rodinia's descendant supercontinents was no gentle story. It was a restless, ongoing rearrangement of Earth's surface. As the global conveyor stirred the seas into rhythm, the continents above continued their slow, inevitable drift. Pangea was breaking apart piece by piece, and in the process, Earth began sketching the rough outlines of the continents we know today. Fact 67. The Atlantic Ocean was born as Pangea cracked. Around 180 million years ago, rifting between Africa and South America and between North America and Europe widened into a true ocean. The Atlantic began as a narrow seaway, but its steady expansion would one day span half the globe. Fact 68. India set off on its lonely journey. Once nestled inside the southern supercontinent Gondwana, India broke away and drifted north at remarkable speeds, at times up to 20 centimeters a year. This long voyage would eventually slam India into Asia, raising the Himalayas. Fact 69. Antarctica and Australia drifted into isolation. As Gondwana fractured, Antarctica began sliding south toward the pole, while Australia moved eastward. Their separation rewired ocean circulation and climate, laying foundations for the cold, icy Antarctica we know today and the unique ecosystems of Australia. These weren't just random rearrangements of rock. Each continental move reshaped ocean currents, wind patterns, and ecosystems. The world was becoming patchwork, a planet of distinct continents, climates, and evolutionary theatres. For life, this fragmentation was opportunity. Isolation created hotspots of adaptation, where species evolved independently, cut off from their relatives on other land masses. It was the beginning of the diversity we now take for granted, a world where the geography itself became a driver of life's endless experiments. And while continents carved their identities above the waves, deep below the seas, something equally dramatic was taking place. The rise of undersea mountains and ridges that would turn the ocean floor into one of Earth's busiest landscapes. While continents carved their outlines above the surface, an equally dramatic story was unfolding below. The oceans were not flat basins. They were being restructured from within as molten rock pushed upward to form ridges, mountains, and entire undersea landscapes. Fact 70. The Mid-Atlantic Ridge began during the breakup of Pangea. As the Atlantic Ocean opened, molten rock rose from the mantle, hardening into new crust. This created the Mid-Atlantic Ridge, a massive underwater mountain chain that still stretches more than 16,000 kilometers, the longest mountain range on Earth. Fact 71. Seafloor spreading reshaped ocean basins. As magma pushed ridges apart, old crust sank back into the mantle elsewhere. This recycling system meant Earth's ocean floor was constantly renewing itself. None of today's seafloor is older than about 200 million years, dating back to Pangea's breakup. Fact 72. Undersea ridges became biodiversity hotspots. Volcanic vents and hydrothermal systems released minerals that supported unique ecosystems. Ancient microbial communities thrived there, showing how life could flourish even in the absence of sunlight. These vent ecosystems are sometimes viewed as analogues for how life may exist on icy moons like Europa or Enceladus. These undersea ridges didn't just build the ocean floor, they reshaped global circulation. Mountains beneath the waves directed currents, altered nutrient flows, and carved invisible boundaries in the seas. In many ways, the breakup of Pangea gave Earth not just new continents, but a whole new ocean world beneath. And as the seafloor grew busier, so too did the surface above. The continents drifting apart carried life in different directions, setting the stage for evolutionary experiments that would take the planet into an age of astonishing diversity. As the continents pulled farther apart, Earth began to split into isolated worlds. What once had been a single connected landmass became scattered arenas where species evolved apart from one another, each writing its own version of life's story. Fact 73. Isolation sparked evolutionary experiments. When South America drifted westward and cut ties with Africa, its animals and plants began evolving independently. This is why, tens of millions of years later, South America would be home to giant ground sloths and terror birds, creatures unlike anything elsewhere. Fact 74. Continental drift explains today's unique ecosystems. Australia's split from Gondwana meant its species evolved without interference from other continents. Over time, this produced marsupials like kangaroos and wombats, creatures that thrived in niches filled by placental mammals elsewhere. Fact 75. Fragmentation increased global biodiversity. Each separated landmass became a stage for new evolutionary dramas. Isolation didn't reduce life's variety, it multiplied it. The diversity of ecosystems we see today, from the Amazon rainforest to Madagascar's lemurs, traces back to these ancient separations. This period of Earth's history reminds us that geography isn't just a backdrop for life, it's a driving force. Where continents go, species follow, and when continents split, species diverge. The breakup of Pangea was more than geology, it was a blueprint for the modern biosphere. And while continents drifted farther apart, something else was shaping life in a quieter way. The slow but steady shifts in climate zones that tested species' resilience and forced adaptation. Even as continents drifted into isolation, the climate above them was constantly shifting. Earth's long-term patterns of warmth, ice, and rainfall were never fixed. Instead, they moved like invisible belts across the globe, following the wandering continents and altering the rules of survival. Fact 76. Continental drift shifted climate zones dramatically. As land masses drifted north or south, they carried ecosystems into entirely new conditions. What was once lush rainforest might slowly turn into arid desert, or cool temperate woodlands might become subtropical swamps. Life had no choice but to adapt, migrate, or vanish. Fact 77. Monsoon systems grew stronger with continental separation. When landmasses like India and Asia began moving apart and later colliding, they altered global wind and rainfall patterns. The growing size of isolated continents allowed monsoon systems to intensify, bringing seasonal floods and dry spells that shaped both landscapes and species. Fact 78. Polar drift reshaped ocean and ice dynamics. As Antarctica slid south toward the pole, it gradually cooled. Even before the great ice sheets formed, the continent's position began influencing ocean currents, setting the stage for the frozen landscapes that would later define it. These shifting belts of climate created an Earth that was both dynamic and unforgiving. Species that once thrived in one zone had to face new trials in another, forcing adaptation at every turn. It's a reminder that life isn't just sculpted by the shape of continents or the chemistry of oceans. It's also carved by the atmosphere above, by winds, rains, and temperatures that follow their own restless rhythms. And while the climate danced across Earth's surface, deep underground, another force was quietly driving the entire process, the slow but unrelenting conveyor of plate tectonics, the machine that keeps continents, climates, and oceans in motion. The drifting continents, the rising ridges, even the shifting climate belts, all of it was powered by one invisible force: plate tectonics. This slow, unrelenting motion beneath our feet is Earth's heartbeat. And during the breakup of Rodinea's descendants and the rise of Pangea's fragments, its rhythm was especially clear. Fact 79. Plate tectonics is driven by convection currents in the mantle. Hot rock deep inside Earth rises, cools as it nears the surface, then sinks again, creating conveyor-like circulation. These currents drag the rigid plates above them, carrying entire continents as if they were passengers on a restless sea. Fact 80. Subduction zones recycle Earth's crust. Where plates collided, one would dive beneath another, melting back into the mantle. This recycling prevented the crust from piling endlessly and fueled the creation of volcanic arcs, like the early precursors of today's Andes or Japan. Fact 81. Plate tectonics maintains Earth's habitability. Without this constant recycling, carbon would remain trapped in rocks or atmosphere. Instead, tectonics balances the carbon cycle, regulating greenhouse gases and stabilizing climate. In effect, tectonics is Earth's thermostat, keeping the planet warm enough for liquid water and stable enough for life. This engine is so fundamental that some scientists argue it may be the defining feature that makes Earth habitable compared to other planets. Mars had volcanism, but no lasting tectonic cycle. Venus has volcanoes, but no moving plates to cool and regulate its atmosphere. Earth alone has this slow, balancing rhythm, and as the plates beneath Rodinia and later Pangea shifted, collided, and tore apart, they not only reshaped land and sea, they sculpted the stage for all of life's great evolutionary dramas. But if tectonics provided the stage, then one particular set of movements would soon dominate the act. India's legendary collision with Asia and the birth of the greatest mountain range the world has ever known. After millions of years drifting north at extraordinary speed, the Indian subcontinent met its destiny. Roughly 50 million years ago, India slammed into Asia, and the impact changed the face of Earth forever. Fact 82. The Himalayas are the product of continental collision. Unlike oceanic crust that sinks into the mantle, continental crust is too buoyant to subduct. When India and Asia collided, their rocks crumpled and stacked skyward, forming the Himalayan range, peaks that continue to rise even today. Fact 83. The Tibetan Plateau became Earth's third pole. Behind the Himalayas, the collision lifted an immense plateau nearly 5 kilometers high. This plateau altered atmospheric circulation, helping drive the Asian monsoon system that billions depend on today. Fact 84. The Himalayas are still growing. India continues to push into Asia at about 5 centimeters a year, causing frequent earthquakes and keeping Everest and its neighbors rising. A mountain range still in motion long after its birth. This collision is not just a story of mountains, it's a story of climate, rivers, and life. The rising Himalayas redirected rain-bearing winds, feeding mighty rivers like the Ganges, Indus, and Brahmaputra. These waters carved valleys, nourished plains, and created one of the richest agricultural regions on the planet. The Himalayas remind us that tectonics doesn't just sculpt landscapes, it engineers ecosystems and human history. Civilizations have risen and thrived at the feet of these mountains, their cultures shaped by the monsoons and rivers born from that ancient collision. And just as the Himalayas rose skyward, other mountain-building events were reshaping Earth on different continents, vast ranges that would one day weather down and scatter minerals across fertile lands. The Himalayas may be Earth's tallest peaks, but they are not its only monuments to collision. Across the planet, Other mountains rose under different circumstances, each carrying a chapter of Earth's restless story. Fact 85. The Andes are powered by ocean-continent collision. Along South America's western edge, the Nazca Plate dives beneath the continent. This subduction zone fuels one of the most volcanically active chains on Earth, the Andes, stretching nearly 7,000 kilometers and still rising. Fact 86. The Rockies tell a different story. Unlike the Andes, the Rockies were shaped by a shallow subduction event. Instead of diving steeply, the oceanic plate slid under North America at a low angle, pushing mountains far inland. This unusual process left a geological puzzle that scientists still study today. Fact 87. The Alps preserve a history of ancient seas. When the African plate collided with Europe, remnants of the Tethys Ocean were trapped and uplifted, folding marine sediments into towering peaks. Fossils of sea creatures are still found high in the Alps, a reminder that these stone giants once lay beneath waves. Together, these mountain ranges highlight the creativity of tectonics. The same engine that raised the Himalayas also sculpted the Andes, Rockies and Alps, but in different ways, under different rules. Each tells us not just about collisions and subductions, but about the adaptability of Earth's crust itself. And while mountains rose, other landscapes told quieter stories. Plate tectonics was also pulling apart land, opening seas and creating rift valleys that looked like scars across the continents. These too shaped the geography of Earth in lasting ways. Not all of Earth's great landscapes were born from plates colliding. Some were born when plates pulled away from one another, leaving deep scars in the crust. These rift valleys, though quieter than mountain ranges, tell stories just as dramatic. Fact 88. The East African Rift is a continent splitting in real time, stretching from Ethiopia down to Mozambique. This rift is Earth's most striking modern example of a continent being torn apart. Volcanoes rise along its length, new lakes fill its basins, and one day, millions of years from now, a new ocean may flood in, dividing Africa in two. Fact 89. Rift valleys are incubators for life. The lakes of the East African Rift, like Lake Tanganyika and Lake Malawi, are home to extraordinary biodiversity, including hundreds of unique cichlid fish species. Geology doesn't just shape land, it carves out cradles of evolution. Fact 90. Ancient rifts left permanent marks. Long before Africa's modern rift, earlier separations helped shape supercontinent cycles. The opening of the Atlantic Ocean, for instance, began as a rift valley between Africa and South America, a scar that widened into a sea and then an ocean. Rift valleys remind us that separation is as creative as collision. Where the crust breaks apart, new landscapes are born, new ecosystems flourish, and the seeds of future oceans are planted. And just as rifts reshaped continents, another force high above was also transforming Earth, the atmosphere itself enriched by life, shaping climate and ecosystems in partnership with geology below. While rift valleys and mountains defined the ground beneath, another force above was just as important. Earth's atmosphere. It wasn't always the breathable air we know today. It evolved in tandem with life itself, shaping climates, oceans, and ecosystems across every age. Fact 91. Oxygen was not always abundant. For most of Earth's history, the atmosphere lacked oxygen. Only with the rise of cyanobacteria during the Great Oxidation Event, billions of years ago, did oxygen slowly accumulate, transforming the air and allowing complex life to emerge. Fact 92. The carbon cycle connects geology to the sky. Plate tectonics doesn't just move continents, it regulates greenhouse gases. Volcanoes release carbon dioxide, while weathering of uplifted mountains and subducted carbonates pull it back down. This delicate balance kept Earth from freezing solid or boiling away, unlike Mars or Venus. Fact 93. Ancient supercontinents altered atmospheric circulation. Rodinia and later Pangea were so vast that they reshaped wind and rainfall patterns on a global scale. Deserts spread across interiors far from the oceans, while coastal edges became the cradles of lush ecosystems. The atmosphere, then, wasn't just passive. It was active, dynamic, and tightly linked to Earth's shifting crust. The breath we take today is the outcome of billions of years of negotiation between rock, ocean, air, and life. And with that air came not only stability, but also vulnerability. Because while Earth's atmosphere nurtured life, it also left life exposed to ice ages, to warming pulses, and to the delicate balance that could tip with each geologic upheaval. Air and rock worked in partnership, but they also sometimes conspired to push life to its edge. Earth's history is marked not only by stability, but by extremes, periods when the balance tipped too far and survival hung by a thread. Fact 94. The snowball Earth episodes were near total freezes. Around 700 million years ago, during Rodinia's breakup, feedback loops of ice and reflection spread glaciers across nearly the entire planet. Oceans may have been sealed beneath thick ice sheets, with life clinging to survival in isolated refuges. Fact 95. Supercontinents drove extreme climate swings. Vast interiors of Rodinia and Pangea lacked moderating oceans, leaving them vulnerable to scorching summers and freezing winters. Dust storms, arid belts, and erratic rainfall cycles challenged ecosystems on land. Fact 96. Greenhouse pulses rescued Earth from deep freezes. Volcanic eruptions continued even during snowball Earth, releasing carbon dioxide that accumulated in the air. Over millions of years, this warming blanket eventually melted the ice, restoring liquid oceans and reawakening climate cycles. These extremes weren't just catastrophes, they were tests. Each time Earth swung from icehouse to greenhouse, life adapted, evolved, and grew stronger. Without those challenges, complex multicellular organisms, and eventually us, may never have emerged. And as Earth thawed from its frozen grip, a cascade of new ecosystems and evolutionary bursts followed, setting the stage for the Cambrian explosion, one of the most extraordinary leaps in the history of life. As the great ice sheets of snowball Earth melted, the stage was set for one of the most dramatic transformations in Earth's history. Oceans, once locked beneath frozen shells, became warm, oxygen-rich cradles of possibility. Life was about to take a leap forward. Fact 97. The Cambrian explosion produced an explosion of body plans. Around 541 million years ago, organisms that had remained simple for billions of years suddenly diversified. Shells, spines, eyes, and complex body structures appeared in rapid succession, filling oceans with new creatures. Fact 98. Oxygen was the fuel for this revolution. With higher levels in the oceans and atmosphere, animals could grow larger and more active. Predation became possible, driving an evolutionary arms race, shells against teeth, mobility against ambush. Fact 99. The Cambrian explosion laid the foundations for nearly all modern animal groups. Arthropods, mollusks, echinoderms, and early chordates all trace their roots to this era. The strange trilobites that scuttled across seafloors were among the most successful of these pioneers. The Cambrian wasn't just an explosion of forms, it was an explosion of ecological interactions. For the first time, food webs grew complex, ecosystems expanded in layers, and competition shaped evolution in ways still visible today. It was as if Earth had unlocked a new level in its long story. From a frozen globe barely holding life together to a vibrant, crowded world teeming with strange and beautiful creatures. And while most of these first experiments in complexity would vanish in time, their legacy lives on in every fish, bird, insect, and mammal. including us. The Cambrian seas were alive with innovation, but Earth's story was far from finished. The next frontier lay just beyond the waves, the land, a place of danger and opportunity. It was empty then, barren rock and shallow soils, but for life, it was a blank canvas. Fact 100. Plants were the first pioneers. Algae gradually adapted to survive at the water's edge, anchoring themselves to moist ground. Over millions of years, these early plants developed sturdier structures, spreading greenery across once barren shorelines. Fact 101. Plants transformed the land and the atmosphere. By pulling carbon dioxide from the air and releasing oxygen, these pioneers reshaped the very air animals would one day breathe. Their roots broke down rocks, creating the first true soils, and in doing so they paved the way for entire ecosystems. Fact 102. Animals soon followed. Arthropods, the same group that produced trilobites, became the first creatures to scuttle onto land. Millipede-like forms left faint trails on ancient sands, a sign that Earth's ecosystems were no longer limited to the seas. This transition wasn't easy. The land lacked the buoyancy of water, so new structures were needed to move and breathe. But every step forward, every route, every footprint marked a milestone in Earth's transformation from an ocean world into a planet with forests, rivers, and eventually civilizations. And as plants and animals gained a foothold on land, they would set in motion changes that echoed through the ages, stabilizing climates, deepening soils, and fueling the cycles of life that would lead to dinosaurs, mammals, and us. Once the first hardy plants crept ashore, they began to change not only the land beneath them, but the very systems of the planet. Over time, those small, simple pioneers grew taller, stronger, and more complex, until entire landscapes were draped in green. Fact 103. The Devonian period saw the rise of the first forests. Around 380 million years ago, primitive trees such as Archaeopteris formed dense woodlands. Their towering trunks stretched higher than anything Earth had ever seen, creating shaded canopies for the first time. Fact 104. Forests transformed Earth's climate. Deep roots stabilized soils, preventing erosion. More importantly, the vast drawdown of carbon dioxide by trees cooled the planet and contributed to major shifts in climate, including ice ages. Fact 105. Forests created new habitats and ecosystems. Rivers that once ran unchecked now wound their way around roots and fallen logs. Swamps became breeding grounds for insects and amphibians. The land was no longer barren, it was alive, layered, and complex. The forests of the Devonian were unlike the ones we know today. There were no flowering plants yet, no buzzing bees, no grass. Instead, ferns, mosses, and spore-bearing trees dominated. Yet even in their alien form, these early forests became powerful engines of change, shaping the surface of continents and the air above them. Forests also brought a profound consequence. They buried massive amounts of carbon, setting the stage for future energy sources like coal. In that sense, the forests of the Devonian are still with us today, powering parts of our civilization hundreds of millions of years later. What began as simple mats of algae had grown into towering ecosystems, and they would change forever how life on land would unfold. Forests weren't just backdrops, they were engines of evolution. By pumping oxygen into the air at levels far higher than today, they set the stage for life to grow to astonishing scales. Fact 106. Oxygen levels peaked during the Carboniferous period. Around 300 million years ago, Earth's atmosphere carried up to 35% oxygen, compared to just 21% today. This made the air highly breathable and allowed animals to grow far larger than their modern relatives. Fact 107. Insects became giants. Dragonflies with wingspans the size of seagulls hunted over swamps. While millipedes longer than cars crawled along the forest floor, spiders and scorpions reached sizes that would seem almost unreal today, all thanks to oxygen-rich air. Fact 108. Amphibians flourished in this lush environment. These early vertebrates, descendants of fish, took advantage of swampy forests. Some grew massive, resembling crocodiles with stubby legs, ruling both water and land long before reptiles or dinosaurs appeared. The Carboniferous forests were alien yet familiar, buzzing with enormous insects, echoing with the croaks and splashes of amphibian predators, and layered with dense greenery that trapped humidity like a greenhouse. But this paradise carried risks. High oxygen made fires more frequent and intense, sweeping through forests with explosive force. Life had grown powerful, but it was also vulnerable to the very systems that sustained it. Still, this was a golden age, when the world belonged not to dinosaurs or mammals, but to dragonflies, scorpions, and amphibians. It was proof that life could adapt to new rules and thrive in forms we would struggle to imagine walking our world today. The Carboniferous world was lush, wet, and alive with giants. But hidden among the swamps was a quieter revolution, one that would eventually shape the future of life on land. Fact 109. Reptiles evolved from amphibian ancestors. Around 310 million years ago, small lizard-like creatures appeared in the forests. Unlike amphibians, they didn't need to return to the water to reproduce. This single step would change everything. Fact 110. The amniotic egg was the breakthrough. Encased in a protective shell, it carried its own water supply, allowing embryos to grow safely on land. Reptiles no longer depended on swamps and ponds for survival. They could roam farther, adapt to drier climates, and spread into new territories. Fact 111. Reptiles became the blueprint for the future. From these early forms would come lizards, snakes, crocodiles, dinosaurs, and birds. The innovation of the amniotic egg was one of evolution's great inventions, a passport to global success. Imagine these small, scaly pioneers slipping quietly among tree roots, their eggs hidden in leaf litter, while giant dragonflies buzzed overhead. They were unremarkable compared to the massive insects or amphibians of their day, but they held an advantage those giants could never match: independence from the water. While forests and swamps dominated the Carboniferous, reptiles began preparing for a different world, one that would grow harsher, drier, and more open. Their story had just begun, but it was a story destined to outlast the giants of the swamps. As the Carboniferous gave way to the Permian period, Earth was shifting once again. Swamps shrank, climates dried, and oxygen levels dropped from their Carboniferous highs. For amphibians and giant insects, this was a crisis, but for reptiles, it was opportunity. Fact 112. Reptiles diversified into many forms during the Permian, from small, lizard-like insect hunters to massive herbivores and sharp-toothed predators. Reptiles adapted to niches that amphibians could not survive in. Fact 113. The Permian introduced synapsids, ancestors of mammals. These creatures, like the sail-backed Dimetrodon, weren't dinosaurs. They were part of the reptile family tree that would eventually give rise to us. Their sail may have helped regulate body temperature, a key adaptation in variable climates. Fact 114. Reptiles mastered dry environments. Unlike amphibians, they could thrive in deserts and semi-arid lands thanks to scaly skin that conserved water and their egg innovation that freed them from ponds and swamps. The Permian landscapes were harsh, red deserts, wide basins, and seasonal extremes. Yet reptiles spread across them, proving that survival wasn't about size or ferocity, but about adaptation. By the end of the Permian, reptiles were no longer fringe players. They were the rulers of the land, reshaping ecosystems and setting the stage for the Mesozoic, the age of dinosaurs. Fact 117. Recovery from the Great Dying took millions of years. Ecosystems collapsed, food chains broke down, and life struggled to rebound. For a time, Earth was nearly silent, its once teeming forests reduced to barren stretches. Imagine standing in a Permian landscape as skies turn red with ash, rivers choke on dying fish, and forests wither under toxic rains. The giants that once ruled, from Dimetrodon to amphibious hunters, vanished almost overnight in geological terms. And yet, despite this devastation, the story of life did not end. A few hardy survivors carried on, clinging to existence. Among them were reptiles, small, adaptable, and ready to inherit whatever world emerged from the ashes. Its eventual crash into Asia, which would raise the Himalayas tens of millions of years later. From this silence, a new age would rise, one of recovery, innovation, and eventually dinosaurs. After the Great Dying, Earth was scarred. Forests were gone, oceans nearly lifeless, and climates unstable. Yet, out of this emptiness came resilience. Slowly, survivors began to rebuild the web of life. Fact 118. Early Triassic landscapes were barren compared to the lush Permian. Deserts stretched wide, vegetation was sparse, and ecosystems were fragile. Plants like conifers and ginkgos began to repopulate the land, offering the first steps toward recovery. Fact 119. Small reptiles became the dominant survivors. In a world of scarcity, size was no longer an advantage. Adaptable, quick-breeding species like early archosaurs, relatives of crocodiles and dinosaurs, thrived in the harsh Triassic climate, but their dominance came at a cost. The Permian world would soon be tested by one of the greatest catastrophes in Earth's history. A mass extinction so severe it nearly ended life itself. Reptiles had spread across deserts, swamps, and forests, mastering a world that seemed to belong to them. But survival on Earth is never guaranteed. About 252 million years ago, the planet faced its most catastrophic crisis, an event so devastating that it came to be known as the Great Dying. Fact 115. The Permian Triassic extinction wiped out around 90% of marine species and 70% of land species. No other mass extinction in Earth's history was as severe. Fact 116. The cause was linked to massive volcanic eruptions in Siberia. For nearly 1 million years, vast lava flows poured from fissures, releasing carbon dioxide, methane, and toxic gases into the atmosphere. These eruptions warmed the planet, acidified oceans, and poisoned air and water systems. From this silence, a new age would rise, one of recovery, innovation, and eventually dinosaurs. After the Great Dying, Earth was scarred. Forests were gone, oceans nearly lifeless, and climates unstable. Yet out of this emptiness came resilience. Slowly, survivors began to rebuild the web of life. Fact 118. Early Triassic landscapes were barren compared to the lush Permian. Deserts stretched wide, vegetation was sparse, and ecosystems were fragile. Plants like conifers and ginkgos began to repopulate the land, offering the first steps toward recovery. Fact 119. Small reptiles became the dominant survivors. In a world of scarcity, size was no longer an advantage. Adaptable, quick-breeding species like early archosaurs, relatives of crocodiles and dinosaurs, thrived in the harsh Triassic climate. The Triassic world was fragile, but it was also inventive. Life was experimenting with new forms, filling niches left empty by the Great Dying. Out of this experimental age, something extraordinary emerged: the first dinosaurs. Fact 121. Dinosaurs first appeared around 230 million years ago in the late Triassic. They were small at first, fast, lightly built, and far from the towering giants they would one day become. Fact 122. The earliest dinosaurs were divided into three groups: theropods, meat-eaters that walked on two legs; sauropodomorphs, long-necked plant-eaters; and ornithischians, early herbivores with specialized jaws. These three lineages would dominate the next 160 million years. Fact 123. Dinosaurs rose quietly, not explosively. For much of the Triassic, they were minor players, living alongside crocodile-like relatives known as pseudosuchians. But their agility, upright stance, and efficient lungs gave them long-term advantages. Picture a Triassic floodplain at dusk. Small, agile theropods prowl among ferns, their shadows stretching long in the fading light. Not yet kings, but destined to be. Herds of early sauropodomorphs browse on conifers, while armoured pseudosuchians lurk by the water's edge. It was a world in balance, but one leaning toward change. The first dinosaurs were not giants. They were survivors, seizing opportunities in a fragile world. Their rise wasn't inevitable, but once it began, it was unstoppable. Soon, the age of reptiles would belong to them. At first, dinosaurs were background players, quick-footed hunters and cautious grazers sharing the land with crocodile-like pseudosuchians. But Earth was about to shift again, tipping the balance in their favour. Fact 124. A smaller extinction at the end of the Triassic cleared the stage. Many of the dominant crocodile-like reptiles disappeared, leaving ecosystems open for dinosaurs to expand. Fact 125. Dinosaurs diversified rapidly in the early Jurassic. Sauropodomorphs grew into giants, their necks stretching toward the treetops. Theropods became swifter and more specialized hunters. Herbivorous ornithischians adapted to tougher plants, shaping entire landscapes. Fact 126. Dinosaurs' anatomy gave them the edge. Their upright legs made them more efficient movers than their sprawling competitors. Their lungs, similar to birds, pumped oxygen more effectively in a low-oxygen world, and their ability to regulate body temperature let them thrive in varied climates. Imagine a dawn scene on a Jurassic floodplain. A herd of long-necked sauropods grazes under towering conifers, their silhouettes rising like living skyscrapers. Nearby, a pack of early theropods stalks across the mist, their calls echoing. In the distance, armoured herbivores shuffle through cycads, reshaping the land as they feed. Dinosaurs had risen from humble survivors to ecosystem engineers. They were no longer passengers in Earth's story. They were becoming its authors, writing the next great chapter of life. By the early Jurassic, dinosaurs were no longer survivors clinging to life. They had become the architects of their world. Their numbers grew, their sizes expanded, and their diversity reshaped entire ecosystems. Fact 127. Sauropods like Brachiosaurus and Diplodocus became the largest land animals in Earth's history. Some reached over 30 meters in length, their necks sweeping across the treetops like living cranes. These herbivores were the backbone of Jurassic ecosystems. Fact 128. Apex predators like Allosaurus ruled the land. Unlike the smaller theropods of the Triassic, these hunters were larger, faster, and equipped with serrated teeth designed to slice through flesh. They patrolled floodplains and forests, keeping herbivore populations in check. Fact 129. Jurassic ecosystems were stable and interconnected. Giant sauropods cleared vast areas of vegetation, which encouraged regrowth and created habitats for smaller animals. Predators thrived because plant eaters were abundant. In turn, ecosystems recycled nutrients more efficiently than in earlier times. Picture a Jurassic Valley at dawn. towering conifers stretch into the mist, while herds of sauropods lumber slowly, shaking the earth with each step. Beneath them, smaller dinosaurs scatter, careful not to be crushed. In the distance, an Allosaurus stalks, its shadow gliding across the forest floor. It was a time when scale defined survival, and dinosaurs had mastered the art of growing vast. The Jurassic was more than just an age of giants. It was proof that life, once shattered by catastrophe, could rebuild into something even more extraordinary. And yet this age of balance was not eternal. While giant sauropods shook the earth and predators like Allosaurus ruled the land, another dynasty was unfolding above, one that would fill the skies with wings. Fact 130. The first true flying vertebrates were pterosaurs. They appeared in the late Triassic but flourished in the Jurassic, with wingspans ranging from small seagull-sized gliders to giants that rivaled modern planes. Fact 131. Pterosaur wings were unique. Unlike birds, which use feathers, pterosaurs had wings supported by an elongated fourth finger. Their membranes stretched thin and strong, allowing graceful flight over coastlines and inland lakes. Fact 132. These flying reptiles reshaped ecosystems. They were the first to hunt insects in the air, fish in shallow waters, and scavenge on land. Their presence connected the skies to every other part of the Jurassic environment, linking earth, water, and air. Imagine a Jurassic cliff at sunrise. Pterosaurs launch into the golden sky, their wings casting long shadows across the ocean below. Some soar high on thermal currents, barely moving their wings, while others dive dramatically into waves, snatching fish in a spray of foam. Their cries echo across the coastline, announcing that the skies, once empty, now had rulers. The Jurassic was no longer just an age of giants on the ground. It was also the first great age of flight, where the heavens themselves became part of Earth's story. But as skies filled with wings, another quieter revolution was beginning on the branches below, one that would eventually give rise to the ancestors of birds. As pterosaurs soared through Jurassic skies, they weren't the only creatures experimenting with flight. Deep in the forests, small feathered dinosaurs were refining a different strategy, one that would eventually reshape Earth's skies forever. Fact 133. Archaeopteryx, discovered in Germany, is considered the first true bird. Living about 150 million years ago, it blended reptilian features like teeth and a long bony tail with bird-like feathers and wings. Fact 134. Feathers did not originally evolve for flight. Early feathers likely provided insulation and display. Only later did they become adapted into aerodynamic surfaces, allowing gliding and eventually powered flight. Fact 135. Archaeopteryx was a bridge between two worlds. It could flap short distances, glide from tree to tree, and perch on branches, behaviors that hint at the gradual transformation of theropod dinosaurs into modern birds. Picture a twilight forest. Ferns sway as a feathered Archaeopteryx leaps from a branch, its wings catching the fading light. It glides silently across a clearing, landing clumsily but effectively on another perch. In the distance, pterosaurs still dominate the open skies, but here in the tangled shadows a new kind of flyer is taking shape. Birds had arrived, not as instant masters of the air, but as experiments in survival, testing what wings, feathers, and balance could achieve. Their quiet beginnings foreshadowed a dynasty that would one day outlast even the greatest giants of the Jurassic. While the skies were filling with wings, the ground was quietly preparing its own revolution. For hundreds of millions of years, plants had been dominated by ferns, conifers, and cycads. But during the late Jurassic and into the Cretaceous, something entirely new appeared. Fragile at first, but destined to transform Earth. Fact 136. The first flowering plants or angiosperms appeared around 140 million years ago. Unlike conifers, which relied on wind to scatter their seeds, these new plants formed blossoms that lured animals to help with reproduction. Fact 137. Flowers evolved alongside pollinators. Insects, already thriving since the Carboniferous, began to form partnerships with angiosperms. Nectar and pollen became rewards, while wings and legs became tools for carrying life from bloom to bloom. Fact 138. The rise of flowers reshaped ecosystems. They spread quickly, adding bursts of colour to landscapes that had been dominated by green. They offered richer food sources for insects, which in turn supported new birds and small mammals. Imagine a clearing where towering conifers still cast deep shadows, but at the forest's edge, delicate blossoms sway in the breeze. Beetles crawl over bright petals. Primitive bees hover, dipping into nectar. Above, a feathered dinosaur perches, perhaps tasting fruit for the first time. The quiet arrival of flowers was more than beauty. It was a new engine of biodiversity. From this point forward, Earth's story would not just be written by giants, predators, or winged rulers. It would also be told by the tiniest blooms, shaping the path for countless species to come, including us. As flowers spread across the Jurassic world, they opened new possibilities for life. But beneath the shadows of giants, another story was quietly unfolding. Small, warm-blooded creatures, the early mammals, were carving out niches of their own. Fact 139. Mammals first appeared during the late Triassic, but in the Jurassic they diversified. They were small, nocturnal, and often insect eaters, avoiding direct competition with dinosaurs. Fact 140. Early mammals like Morganucodon were tiny, mouse-sized animals with sharp teeth adapted for insects. Their keen sense of smell and hearing helped them survive in the dark while predators roamed by day. Fact 141. Warm-blooded metabolism gave mammals a survival edge. They could regulate their body temperature, hunt at night, and remain active in cooler climates where reptiles slowed down. Picture the forest floor at dusk. Flowers sway above, insects hum through the undergrowth, and in the quiet, a tiny mammal darts from its burrow. Its whiskers twitch, ears flick toward every sound. It scurries across roots, searching for food, always cautious of talons and teeth waiting above. They were not yet rulers of the earth. They were survivors, learning in shadows, thriving in margins. But from these humble beginnings would rise an entire lineage that one day would inherit the planet. While flowers blossomed and mammals crept through the undergrowth, the foundations of Earth were moving slowly, almost invisibly. Deep beneath oceans and forests, the plates of the planet drifted on molten currents, setting the stage for another transformation. Fact 142. Long before the age of dinosaurs, Earth's landmasses had already come together in an earlier supercontinent, Rodinia. It formed nearly 1.1 billion years ago and eventually broke apart about 750 million years ago. Fact 143. The breakup of Rodinia influenced everything from ocean circulation to early animal evolution. Its fragments drifted across the globe, creating isolated environments where life experimented and diversified. Fact 144. These drifting continents slowly reassembled into a new supercontinent, Pangea. By the late Paleozoic, almost all land on Earth was locked into one massive landmass, surrounded by the vast Panthalassa Ocean. Imagine the view from space. Slowly, across millions of years, the outlines of continents slide and merge like puzzle pieces on a glowing blue sphere. Forests come and go, seas open and close, mountain chains rise and deserts spread. To the creatures below it was too slow to notice. But over geologic time, these movements would determine where life thrived. where it vanished, and where new chapters began. The mammals, the flowers, even the soaring reptiles, all were shaped not just by their own struggles, but by the restless continents beneath them. The stage was shifting, and with it, the drama of life itself. With the continents drawn together into Pangea, Earth looked unlike it ever had before. Nearly every landmass was fused into one enormous supercontinent, stretching from pole to pole, surrounded by the endless Panthalassa Ocean. From space, it was majestic, a single sprawling puzzle piece. But for life on the ground, it was both an opportunity and a challenge. Fact 145. Pangea's size created extreme climates. With so much land far from the moderating influence of the sea, the interior of the continent was blisteringly hot by day and freezing by night. Deserts larger than anything today stretched across its heart. Fact 146. Ecosystems were interconnected in ways never seen before. Creatures could walk from one end of the supercontinent to the other without crossing oceans. This allowed reptiles and amphibians to spread widely, filling niches across thousands of miles. Fact 147. Pangea's vastness also meant vulnerability. When environment shifted, whether through drought, volcanic activity, or climate swings, entire regions of species could be wiped out, with fewer barriers to slow the spread of change. Picture a sweeping desert plain under a burning sun. Sandstorms whip across the horizon while hardy reptiles scuttle between sparse plants. Elsewhere, colossal river systems carve through fertile valleys, feeding lush forests teeming with amphibians and early reptiles. Life on Pangea was not uniform. It was a world of extremes where survival depended on adaptation to climates harsher and broader than anything seen before. Fact 120. The Triassic saw the rise of new ecosystems. As life stabilized, niches reopened. Amphibians returned in modest forms, reptiles diversified, and oceans slowly filled again with mollusks, fish, and marine reptiles like the dolphin-shaped ichthyosaurs. The Triassic was not a paradise, it was a crucible. With fewer competitors, survivors experimented with new forms. It was here that the roots of dinosaurs, pterosaurs, and even mammals began to take shape. Imagine barren red deserts with scattered conifers, rivers sluggish under a hot sun, and small reptiles darting across sand dunes. Life was fragile but persistent, taking cautious steps back from the brink. The world had been nearly erased, but in its recovery, evolution was rewriting the script, laying the foundation for one of the most spectacular ages in Earth's history. Pangea gave creatures room to expand and explore, but it also set the stage for the next great upheavals in Earth's story. And like every act before, its reign as a supercontinent would not last forever. For millions of years, Pangea seemed immovable, a world where deserts stretched endlessly, rivers carved deep valleys, and reptiles ruled from one horizon to the other. But beneath its surface, the same forces that had built it were slowly conspiring to tear it apart. Fact 148. Heat trapped beneath Pangea's massive crust created immense tectonic pressure. Over time, this pressure weakened the bonds holding the supercontinent together. Fact 149. Around 200 million years ago, rifts opened in Pangea's heart. Magma welled up from the mantle, tearing the land into pieces. What began as cracks eventually became the birthplaces of new oceans. Fact 150. The Atlantic Ocean owes its origin to this breakup. As the land masses drifted apart, water rushed in, shaping a new marine frontier that continues to widen today. Imagine standing on the edge of one of these ancient rifts. The ground shudders, splitting apart, molten rock glowing in the cracks as fire meets sky. Over thousands of years, those fissures widened into valleys and valleys into seas. Forests that once stretched unbroken were divided, isolating species and rewriting the map of evolution. The breaking of Pangea was not a single event, but a long, drawn-out drama, a reminder that continents are never final, only temporary arrangements in a restless earth. And just as Pangea gave birth to deserts, forests and rivers, its breakup would seed new oceans, new climates and new pathways for life to travel. As Pangea began to tear apart, it didn't just shape valleys and rifts. It wrote a whole new chapter in the planet's oceanography. Fact 151. The Panthalassa Ocean that once surrounded Pangea began to split into smaller seas. This change redirected currents, altered climate, and created new coastlines for life to occupy. Fact 152. The newborn Atlantic Ocean started small, little more than a widening rift valley filled with water, but it would go on to become one of the most powerful oceans on Earth. Today, it drives weather patterns across 2 continents, but its origins trace back to Pangea's undoing. Fact 153. Ocean circulation during the breakup drove evolutionary opportunities. New coastlines meant new shallow seas where marine species flourished, while land animals followed rivers and deltas into fresh territories. Picture this transformation. Coastal cliffs crumbling as seawater rushes into newly opened basins, creating fertile estuaries where early fish species thrive. Across the land, reptilian herds adjust to new migration paths as shifting rainfall patterns change where rivers flow. The same geological forces that cracked Earth's crust also reshaped the very web of life, opening new corridors, closing others, and sparking evolutionary experiments that would ripple forward for millions of years. The breakup of Pangea wasn't destruction, it was creation, carving out the geography that still guides our oceans, climates and ecosystems today. And yet it was only the beginning of an even more complex planetary drama. The breakup of Pangea didn't just redraw coastlines, it rewrote the skies. Fact 154. As new oceans opened, they created fresh pathways for winds and water vapor, birthing new weather systems. Rain began to fall where deserts once baked, and storms raged where calm skies had stretched for millennia. Fact 155. Monsoon-like cycles became more powerful. The contrast between vast land masses and newly formed seas generated intense seasonal rains along coastlines, transforming barren lands into fertile corridors for life. Fact 156. Polar regions shifted dramatically. As Pangea broke apart, ice caps formed and melted in cycles, sending ripples through global sea levels and climate stability. Imagine standing at the edge of a newborn ocean as dark clouds gather above. Lightning forks across the sky and rain hammers the land, carving fresh rivers through young soil. In the interior, once dominated by heat and drought, storms creep further inland, reshaping ecosystems one season at a time. Creatures that once adapted to endless dryness now face wet cycles, forcing new strategies for survival. The skies became storytellers of change. Winds and waters carried seeds, shaped migration, and dictated the success or collapse of ecosystems. In this way, the breakup of a supercontinent wasn't only written in stone, it was etched in clouds, storms, and shifting rains. And as Earth's climate system evolved, it continued nudging species toward both struggle and innovation. Life adapted, but it also braced for the next great chapter, the age of dinosaurs, which would inherit this ever-shifting stage. With oceans rising and storms carving new landscapes, Earth offered life something it hadn't seen in millions of years: fresh habitats. Fact 157. Newly formed coastlines created vast, shallow seas, perfect incubators for biodiversity. Coral-like organisms spread across these warm waters, building the first reef systems that would later anchor entire marine communities. Fact 158. Estuaries and river deltas acted as crossroads of evolution. The mixing of fresh and salt water gave rise to adaptable species, from hardy fish to amphibians that thrived in shifting tides. Fact 159. On land, vegetation followed water. Where monsoons brought fresh rains, lush forests sprouted, opening niches for insects, reptiles, and early mammal-like creatures. Picture this: a coastline that didn't exist 1,000 years before, now buzzing with new life. Shallow waves ripple over coral beds, while primitive fish dart between plants. Above, rain-fed forests creep outward, their canopies sheltering insects the size of dinner plates. Each shift in geology acted like a reset button for ecosystems, encouraging life to try new forms, new behaviors, and new strategies for survival. This was a world of experimentation. Some species thrived in the estuaries, others in the forests. Some failed, disappearing as quickly as they appeared. But each attempt added to the complexity of life, building the foundation for future dynasties, including the reign of dinosaurs still to come. The breakup of Pangea wasn't just Earth tearing itself apart, it was Earth reinventing itself, giving life a brand new stage to perform upon. Every new environment created by the breakup of Pangea came with opportunities and risks. Fact 160. Marine reptiles like ichthyosaurs and plesiosaurs thrived in the expanding seas. They filled ecological roles similar to modern dolphins and whales, becoming dominant predators of shallow oceans. Fact 161. Many amphibian lineages struggled. As dry land expanded and wetlands shifted unpredictably, species that relied on constant water lost ground to reptiles better adapted to drought and fluctuating conditions. Fact 162. Insects exploded in diversity. With forests spreading and new plants adapting to varied climates, giant dragonflies, beetles, and early pollinators flourished, shaping ecosystems from the ground up. Imagine diving into one of these newborn oceans. Shoals of fish scatter as a massive ichthyosaur darts through the water, streamlined like a torpedo. Above the waves, insects hum in swarms across lush coastal forests, feeding reptiles that now stalk the land. But in the shrinking wetlands, amphibians cling desperately to survival, unable to match the adaptability of their reptilian cousins. The Earth was no longer a uniform stage. It was patchwork. Wet coasts, arid interiors, storm-swept forests, and frozen poles. Species had to specialize or vanish. Some rose to dominance, while others disappeared forever. The shifting fortunes of life mirrored the restless movements of the continents themselves. And with every turn of this planetary wheel, Earth was preparing for its next headline act, the evolutionary rise of dinosaurs. Earth's story didn't stop with Pangea, nor with the oceans that split it apart. In fact, geologists now believe our planet has always followed a rhythm, the rise and fall of supercontinents in a repeating cycle. Fact 163. Rodinia wasn't the first supercontinent, and it wouldn't be the last. Before it, there was Nuna, sometimes called Columbia. After it, Pangea would come, uniting the world again, only to break apart once more. Fact 164. This cycle, known as the supercontinent cycle, operates on timescales of about 500 to 700 million years. Like a slow heartbeat of the planet, continents drift together, fuse into giants, then fracture into scattered pieces. Fact 165. The breakup of one supercontinent often sets the stage for the birth of another. As oceans open and close, subduction zones drag land masses back together, pulling them into new collisions. Picture Earth as a restless puzzle, never content to keep the same shape. The same process that tore Rodinia apart would later assemble Gondwana and Laurasia, and eventually unite them into Pangea, and today, the very movement of continents we measure with satellites is already laying the groundwork for a future supercontinent, perhaps 200 million years from now. The land beneath your feet isn't permanent. It's part of a vast cycle far older than humanity, and it will continue long after us. It's one thing to imagine supercontinents forming and breaking apart. It's another to prove it. Geologists don't just guess. They follow trails left behind in the very bones of the planet. Fact 166. Paleomagnetism is one of the key tools. As lava cools, the iron within it locks in the direction of Earth's magnetic field, like tiny compass needles frozen in stone. By studying these ancient signals, scientists can reconstruct where continents once sat millions of years ago. Fact 167. Mountain ranges also carry the story. When continents collide, they crumple, leaving behind belts of rock like scar tissue. The Appalachian Mountains in North America and the Caledonian Mountains in Europe are distant relatives, fragments of the same ancient collision. Fact 168. Fossils act as passports of past worlds. Identical species found on now distant continents, such as early reptiles and plant life, reveal that these lands were once neighbours before oceans grew between them. It's a detective's puzzle on a scale that dwarfs human history. Each mineral, each fossilized fern, each seam of coal is like a page from a book that Earth has tried to erase. But not completely. Piece by piece, researchers stitch the story together, showing us how Rodinia existed, how it broke, and how the continents we know today came to be. And just as we read the past from these clues, we can also glimpse the future. If continents have always danced, then their next embrace is already written in the slow drift of tectonic plates beneath our feet. We might think of Rodinia as something long gone, erased by time, but its fingerprints are still here, written into the landscapes beneath our feet. Fact 169. Some of Earth's richest mineral deposits trace back to Rodinia's tectonic shifts. When continents collided, they drove molten material deep underground, forming seams of copper, nickel, and rare earth elements we still mine today. Fact 170. Ancient rift valleys carved during Rodinia's breakup survive as scars in today's continents. In North America, the mid-continent rift, a massive tear that began but never fully split the land, still stretches more than 2,000 kilometers beneath the surface, quietly shaping the geography of the Midwest. Fact 171. Even the stability of our modern cratons, the oldest cores of continents, comes from Rodinia's collisions. These shield regions, in Canada, Africa, and Australia, owe their resilience to the deep welding that happened hundreds of millions of years ago. So when you walk across mountain ranges or when your phone relies on rare metals, you're touching echoes of Rodinia. This supercontinent may be gone, but it continues to influence human history in surprising ways. When Rodinia began to fracture, it wasn't just continents that changed. Life itself felt the ripple. Fact 175. The breakup of Rodinia reshaped coastlines, creating vast new shallow seas. These shallow marine environments became cradles of biodiversity, rich in sunlight and nutrients. Fact 176. In these seas, early multicellular life began to diversify. While still simple compared to today's organisms, algae, sponges, and tiny multicellular forms spread into the ecological niches Rodinia's breakup had created. Fact 177. Oxygen levels in Earth's atmosphere and oceans rose significantly during this time. With more coastlines and more photosynthetic organisms, the planet's chemistry shifted, laying the groundwork for the Cambrian explosion that would soon follow. The breakup of Rodinia wasn't only a geological drama, it was a biological turning point. Every coastline carved by shifting plates was an invitation for life to expand, evolve, and prepare for the burst of complexity just around the corner. Rodinia is long gone. Its mountains have eroded to dust, its rift valleys filled with seas, and its continents scattered across the globe. But the fingerprints it left behind are still everywhere. Fact 178. Many of the world's ancient cratons, the oldest, most stable parts of continents, were shaped by Rodinia's assembly. Without it, the backbone of our modern continents would look entirely different. Fact 179. The oxygen boost and shallow seas from Rodinia's breakup set the stage for the Cambrian explosion. Within a geological blink, life went from simple multicellular forms to the dazzling complexity of animals, plants, and ecosystems. Fact 180. Rodinia's cycle is a reminder that Earth's continents are never still. Every supercontinent, Rodinia, Pangea, and the ones yet to come, is part of a repeating rhythm written into our planet's crust. Rodinia may have existed nearly 1 billion years ago, but its story lives on. In the air we breathe, the minerals beneath our feet, and the life that thrives on shifting ground. When we trace its tale, we're reminded that our planet is not fixed, but forever changing. And somewhere deep in Earth's mantle, the slow work of the next supercontinent has already begun.